In this video, I introduce a deep inverse reinforcement learning. Inverse reinforcement learning is used to find the real-world function hidden in the expert demonstrations. Because the real-world structure in the Markov decision process is not observed. So if we assume a real-world function is linear, so we can express this real-world function as a product of parameter theta and the state or feature vector x. So the problem is easy. However, if R is a nonlinear function, it's not easy to define a complicated function to express this real-world R. In this case, deep neural network is the best choice. Because we use this deep neural network, we can describe the very complicated relationship between the input state and the real-world function. However, we cannot just use this real-world function to determine this model parameters state, because in reinforcement learning, the real-world function is related to the agent policy. So we need to combine real-world R and the agent policy together to determine this model parameters theta. That means from this convergence model parameters, we can determine what's the optimal policy and then calculate this real-world function R. To do so, we use this joint conditional probability P. And then that means at each state, and we can form this theta, we find the R, and at the same time, we let the agent policy close to the expert policy. If we view this as the posterior through the Bayesian theory, then now we can use the expert demonstration data to train the model, find this convergence theta, from theta calculate R, and from theta we know the agent policy close to the expert policy. However, if expert generates the demonstrations not using the optimal policy, because bias, variance, or the system noise, or dynamic environment, usually agent generates the trajectories using suboptimal policy. That means even we find this feature counts and the expert policy, and this feature counts and the agent policy. However, for this suboptimal policy, that means this relationship not a one-to-one relationship. So that's why we need a maximum entropy method to find this P, because and define entropy over this P. What we need to select, we use the maximum entropy to select distribution, make this entropy maximum. And from the entropy, and then we know this is the make sure this log P can make sure the distribution P with have a maximum entropy. And then we use this this as the loss function. Use the chain rule, we got two terms. And this term is just like the regularization. And the main challenge is this part. To use the gradient descent method to update the model parameters, we need to calculate the gradient of this loss function. That means we need to calculate each term, the gradient for each term. And then we put together to get the gradient of the loss function. Like I mentioned, the second part is easier because suppose we use L2 regularization, then now we get a very simple formulation gradient. The most challenging is the Foster part. Foster part, we use the chain rule again. And then now we express this Foster part as the difference between the feature counts and the export policy and the feature count and the agent policy. So that means if we train a model, neural network model, then we use this as a difference, use the back propagation goes through this network. Now each time we improve this parameter theta, and also we improve this feature count and the agent policy. When this is convergent, then now we get the agent policy very close to the export policy. And then now we use this theta to calculate the reward function. That's the idea. So now the major problem is how can we calculate this feature count and the agent policy. From this definition, this is equal to this. This is the probability distribution. We need to calculate the expectation of this probability distribution over all the trajectories. And then now from the definition, then now we know this probability distribution expressed as this part is a partition function, and this part is exponential. It's from the cumulative reward over the trajectory sigma. That means the main problem is how we can calculate this partition. This partition includes all the possible trajectories in the system. Here I use 4 steps to calculate this partition function. First, at the state S, and then select this action A. At this A, we calculate all the, this Z along all the possible trajectories. That means from this point until the terminal point, we use a backward path to calculate, along each possible trajectory, calculate this Z. Because at this state, we have under policy pi, we have so many actions. So we need to add them, all of them together. There's a second step. Third step of this time, because in the time domain, that means at a state, the signal travel from current state to the terminal. And each time we need to update the Z value at this state. So then now we calculate the Z at each time step, we calculate the sum of over the time. This is just for one state. For all the states, we need to, calculate over this state in the domain. And then we get this partition function. For this numerator, it's just exponential. This from this cumulative reward is only at S and A. That means at this state, by selecting this action A, only we calculate expectation at this point until to all the possible terminal states. Once we get this probability distribution, then we can substitute this P in this feature count and get this feature count, and you substitute this feature count into here. This is the feature count and the export policy. And then we use this difference propagates to from the output into the neural network. So once we need use this gradient of the loss function to update the model parameters theta step by step, and each step will improve this feature this feature counts under the policy, under the agent policy. So this means the agent policy is closer to the export policy at each iteration. Finally, when we get the convergent model parameters theta, that means this policy, agent policy, close to the export policy. And then we use the convergent theta to calculate the real world R. And then we use the R in the reinforcement learning to find the optimal policy for agent. For more details, please check with this reference. Thank you. Bye.